This video provides background information for the lab session on the rheological characterization of water-based drilling fluids. Fluids at a given temperature and pressure can be characterized by their behavior under transient conditions as manifested by their response time to changed conditions of flow, their behavior in laminar flow as characterized by their experimental flow curve or rheogram, the constant coefficients of the equation of flow represented by this curve are rheological parameters, which are specific to a particular fluid, their behavior at rest, as manifested by gel formation after a certain period of time for a thixotropic fluid. A fluid is thixotropic if it forms a gel after being shaken and left to stand. It returns to its original condition after it has been shaken again. In general, rheological behavior of the matter can be described using a shear stress to shear rate diagram. In other words, a rheogram. When fluids are flowing, there exists a force that opposes the flow. This flow is called shear stress, and it is represented by a lowercase tau. Shear stress is a measure of frictional drag that occurs between fluid layers A and B. It is expressed as force per unit area. In other words, dynes per centimeter squared. When a force is applied to the movable area of a known area, this plane moves at some velocity. Fluid layers cannot move across adjacent planes. Instead, fluid layer A moves over fluid layer B. Fluid layer A will have a velocity greater than fluid layer B. The velocity of each successive layer progressively increases from the wall to the center of the pipe. The rate at which one layer is moving past its neighbor is known as shear rate. It is represented by a lowercase gamma. Generally, rheological behavior of matter can be described by using a shear stress to shear rate diagram. Depending on the shear stress versus shear rate characteristics, the fluids can be classified as either Newtonian fluids or non-Newtonian fluids. The fluid shows Newtonian characteristics if the shear stress versus shear rate relationship is linear with the constant slope of the line being equal to the viscosity. If the shear stress unit is given in dynes per centimeter squared and the shear rate is given in inverse seconds, the unit of the viscosity is then equal to dynes second per centimeter squared, or poise. In field units, centipoise is commonly used for reporting drilling fluid viscosity. The fluid shows non-Newtonian behavior if the shear stress versus shear rate relationship is not linear, where the viscosity changes as a function of the shear rate. The equation for the rheological models commonly used for describing drilling fluid rheological behavior are shown here. Flow behavior parameters such as consistency index, yield stress, plastic viscosity, and flow behavior index can be determined from lab measurements. The following factors have a direct bearing on plastic viscosity: the amount of solid particles, the size of solid particles, the distribution of solid particles, and the shape of solid particles. For practical purposes, plastic viscosity depends upon the concentration of solids in drilling fluids. Plastic viscosity is also a function of the viscosity of the fluid phase. The yield point or yield stress is part of the flow resistance of the fluid caused by electrochemical forces within the fluid. The forces are due to the charges on the surface of the reactive clays and submicron particles in the presence of electrolytes. Gel strength is a measurement of the electrochemical forces within the fluid under static conditions. A 6-speed viscometer provides measurements at 3, 6, 100, 200, 300, and 600 RPM. The dial reading of the rotational viscometer is defined as theta sub n, where n is the rotational speed of the viscometer. Utilizing rotational viscometer readings, shear stress and shear rate can be calculated. Shear stress can be calculated by multiplying 1.067 by the viscometer dial reading. Likewise, shear rate can be calculated by multiplying 1.703 by the rotational speed of the viscometer. The following parameters are calculated using viscometer readings: plastic viscosity, apparent viscosity, yield point, flow behavior index, consistency index, and gel strength. The apparent viscosity, defined as mu sub A of drilling fluids and cement slurries, is to be determined in accordance with API standards. The apparent viscosity is to be expressed in centipoise. Apparent viscosity is rotational viscometer at reading at 600 RPM divided by 2. Other flow behavior parameters, such as plastic viscosity, yield point, flow behavior index, and consistency index, can be determined by using viscometer readings as follows. Thixotropy, in other words, the change in rheological behavior as a function of time, can be estimated by observing the changes in strength taking place in a gel as a function of time. According to API RP13B, two values, 10 seconds gel strength and 10-minute gel strength, are determined in 6-speed fan viscometers. To measure these, the rotor is run at 600 RPM for 30 seconds, then the motor is stopped for 10 seconds. After 10 seconds have elapsed, the rotor is run at a speed of 3 RPM and the scale deflection is noted a 10-second gel strength in pound force per 100 feet squared. For the 10-minute gel strength, repeat the same procedure as for the 10-second gel strength, but this time a period of 10 minutes is allowed to pass without disrupting the mud. The maximum scale deflection is equal to the 10-minute gel strength in pound force per 100 feet squared. Desirable gels build rapidly and stabilize with time. Typical gel strength values are reported in this slide. Here the first number refers to the 10-second and the second number refers to 10-minute gel strength. Depending on the variation of the values, the gels can be classified as good gel, progressive gel, flat gel, and fragile gel. Example values for good gel, flat gels, progressive gels, and fragile gels are shown here. There are two common rheological models that can be chosen, either closest to the Bingham plastic model or closest to the power law model. In most cases, it is impossible to make this choice based on the shape of the curve alone, regardless of if it is plotted in Cartesian or logarithmic coordinates. The 6-speed fan viscometer provides only 4 experimental points. The readings at 3 and 6 RPM cannot be used if a fluid has a yield point, plug flow, or if it is thixotropic. The experimental points can be used for linear regression in Cartesian coordinates for the Bingham plastic model or logarithmic coordinates for the power law model. The model with the correlation coefficient closest to unity will be chosen for the subsequent calculation. The correlation coefficient can be calculated by the equation shown. This concludes the video providing the background information on the rheological characterization of water-based drilling fluids, and in the next video, we will see the experimental procedure.